Thank you for the opportunity to speak to you today about nature's role in climate change solutions. I'm really thrilled to be able to present this material in the context of the JapanPrize and to continue it as a part of my expression of thanks to the JapanPrize Foundation and the nation of Japan. For today, there are 4 topics that I want to share with you. The first is why we know with a high level of confidence that to solve the problem of climate change, emissions of carbon dioxide need to drop to 0. That's different than dropping substantially. That's different than dropping by 80%. They need to drop all the way to 0. Second, I want to share a personal journey about finding what had been called the missing sink, where a very large fraction of our emissions of carbon dioxide from industrial activity and agriculture had been very difficult to find, and how we eventually found them and why they contribute to nature's role in solving climate change. The third topic I want to talk to you about is essentially protecting this mixing sink, or what we now call the background sink on land. And then finally, I want to translate that into a topic that we call natural climate solutions, how we as stewards of the environment and as soldiers in the fight against climate change can utilize nature to help us provide solutions, and how much we can expect from that, and how we should expect to be able to come up with a credible way to put that into carbon accounting. Let me turn first to this topic of why CO2 emissions need to drop to 0. One of the most clear, most convincing conclusions of recent climate and carbon cycle science is that there's a strong, essentially linear relationship between the total amount of carbon dioxide that's been emitted from industrial activities from the beginning of the Industrial Revolution until whenever we stop, and the amount of warming that occurs. If we want to know what the CO2 budget is for the 2C target, you can simply read across to the level of cumulative lifetime CO2 emissions that are consistent with this 2C target, and it turns out to be something around 3,600 billion tons. Given that we've already emitted a little more than 2,400 billion tons, there's approximately 1,070 billion tons of lifetime CO2 emissions remaining until emissions need to drop to 0 if we want to have a 66% probability of limiting warming to 2C or less. That's a very challenging number to achieve because recent emissions have been on the order of between 40 and 45 billion tons of CO2 per year, meaning that that 2C target represents something like 20 to 25 years of current emissions. And after that, there's no budget remaining. If we look at the widely discussed 1.5 degrees Celsius target, the situation is even more challenging. For a 66% probability of limiting warming to 1.5 degrees Celsius or less, the total lifetime budget is around 2,800 billion tons of CO2. And as of the end of 2021, we have about 320 billion tons of emissions remaining, a little less than 8 years at current emission rates. And again, the challenge is that that's a lifetime emissions budget. Doesn't matter if we slow down emissions. It doesn't matter if we speed them up. When emissions surpass that cumulative total level, we're committed to that level of warming essentially indefinitely in the future. And let me provide another way of looking at the situation that provides a little more graphic evidence of how challenging the emissions reduction task we face is. Here's the trajectory of the growth of CO2 emissions from coal, oil, natural gas, and flaring and cement since before the beginning of the Industrial Revolution. And as you clearly see, emissions growth has been very rapid in recent decades. If we take the total cumulative remaining amount and say we were to spend it over coming decades in a way that decreased very rapidly to zero, it would look like this for the 2C budget. Emissions would have to drop to zero by the 2080s with incredibly rapid rates of decrease that are in fact more rapid than recent rates of growth. If we look at the 1.5C target, the challenge is even more daunting, and emissions would need to drop to zero sometime between 2040 and 2050 at a rate that, in the context of the historical growth, is almost impossibly rapid. It is especially daunting in the context of an emissions budget that we don't believe has even peaked yet, let alone begun to start downward. And remember, every year of continuing emissions at the 2021 rate takes away about 1/8 of the remaining budget. So there's no question that we face a daunting challenge in emissions reduction. But there's also no question that we have many of the technologies necessary to be successful at maintaining a sustainable climate with a total level of warming that's someplace between the 1.5 and 2C, hopefully consistent with the Paris Agreement target of well below 2 degrees Celsius. And what I want to spend the rest of the time today on is talking about how nature can be an asset in reaching that solution. So for a long time, beginning back in the 1970s, Dave Keeling, who was the originator of the high-quality global carbon dioxide measurements, realized that there was a frustrating deficiency in the way that the CO2 budget could be put together. In principle, the annual increase in atmospheric CO2 should be equal to industrial emissions plus emissions from land use minus what goes into the ocean. And the CO2 that goes into the ocean can be calculated relatively accurately just based on the concentration difference between the atmosphere and the ocean. It can also be calculated relatively rapidly, accurately, based on what we see as the rate of CO2 dissolution into the ocean based on the atmospheric pollution from radioactive carbon that was a result of atomic bomb testing. And it very rapidly became clear back in the early 1970s that this calculation wasn't balancing, that there was less carbon dioxide in the atmosphere than one would expect based on the numbers. And what Keeling and others identified was a missing sink. Something in the Earth system was removing CO2 from the atmosphere at a substantial rate, even back in the 1970s. And much of my career in the last 40 years has been focused on trying to identify the sources and locations of this missing sink. And we've done it lots of different ways. One of the ways we pursued the causes behind and the magnitude of the missing sink was with empirical studies where at the landscape scale we fumigated, in this case grassland in California, an area with increased atmospheric CO2, and we looked for changes in plant growth. We also added nutrients and water and changed the temperature and tried to understand the basics of how ecosystems responded to a changing climate and whether ecosystems on land might be contributing to this missing sink. We also converted a lot of those empirical measurements into mathematical models that utilize satellite data to get an idea of where plants were growing rapidly and where they weren't. And based on that model, we're able to calculate global rates of plant growth here on the land and in the oceans, and documenting that by far the highest rates of plant growth were in the world's tropical forests, but there were very active areas of plant growth on an annual basis in eastern North America, throughout much of Europe, and in much of East and Southeast Asia. That provided an indication that there was important potential for carbon dioxide storage in areas with rapid plant growth, but it didn't identify where it was. The next thing we did to try and figure out where the storage was occurring was to look at the forest inventories, which in the world's rich countries are kept with a high level of accuracy and have been maintained in many cases for 100 years or more, mainly as a service to the forest industries. And we realized that there were important rates of carbon uptake in most of the Northern Hemisphere countries, with the largest carbon uptake being in the United States and in the former Soviet Union and Europe, and that some areas of the Northern Hemisphere that one might expect to be benefiting from a warming climate, in fact, weren't. Canada was, by 2002, already a net source of carbon to the atmosphere as a result of already increase in forest fires and insect outbreaks. This kind of analysis pointed strongly to the temperate forests of the Northern Hemisphere as being an important location for this missing sink, and indicated that it could explain part, but not all, of the extra carbon uptake in the calculation that Keeling did back in the 1970s. So the next thing we did was we tried to utilize atmospheric models that allowed us to estimate the locations of carbon uptake and loss based on the pattern of concentrations in the atmosphere using a set of techniques called inverse modeling. And based on that, what we found was that the total estimated rates of carbon uptake, this was for the continental United States, more or less matched the estimates from the inventory type data that I showed you earlier, which is based on foresters going around and measuring trees with diameter tapes. The land-based range was around 500 million tons of carbon per year, and the estimates based on the atmosphere with a whole bunch of different techniques indicated with different colored and sizes of symbols, more or less clustered around those forestry-based techniques, indicating that at least for the United States, where we could combine the two techniques, there was a good indication that there was a strong sink. And the fact that the forestry data so clearly pointed at the strong sink indicated that at least some of it was probably due to the historic regrowth of forests that had been deforested decades earlier, and that it wasn't all due to a changing climate or to fertilization by increasing atmospheric CO2. So as we did more and more work, it became clear that the background sink, or this missing sink, really was located in the world's forests, and that it was caused by several things. Initially, Keeling thought that it might be caused entirely by the increase in CO2 in the atmosphere acting as a fertilizer for the plants. But it turned out, based on our studies of CO2 fertilization and lots of other people's work, that that could only explain a modest fraction of the sink, and that a substantial fraction was due to past land use, and that as we look forward, we're looking at a situation in which the dynamics of this missing or background sink will be controlled by a combination of the response of different kinds of ecosystems to CO2 fertilization, the responses to a changing climate, and the historical legacies of land use. It was also surprising that the estimates of the location of this missing sink put it quite squarely in the middle latitudes of the Northern Hemisphere, which wasn't the areas where the plants were growing most rapidly, but it's the areas where the human imprint of past land use has had the biggest impact. And the other thing that was really striking was that this background sink is not a small fraction of the total global carbon budget. It turns out that it's a really big factor in the rate of increase of atmospheric CO2, and it's something that we need to focus on squarely when we think about solving the climate challenge. Here's a picture of the way that the distribution of CO2 has unfolded over past years. You can see in the top part of the figure the gray band going from the middle of the 19th century, about 1850, to the present. The emissions from fossil fuel, this parallels the pattern that I showed earlier. You can see the flux in the brown band from land use change, deforestation, which in the 19th century was mainly in the temperate zone, and in the 20th and 21st century has been mainly in the tropics. Those two bands above the middle horizontal line are sources of CO2 to the atmosphere. And below the horizontal line, you can see where the CO2 is gone. The bottom light blue band is the atmosphere, and that's the increase in carbon dioxide in the atmosphere, the carbon dioxide that's causing the warming that we're seeing around the world. The dark blue band is the amount of CO2 that's gone into the oceans, and that amount has been relatively stable from year to year, but it's been increasing as the atmospheric CO2 has increased. And we can calculate that with a relatively high level of confidence. The remaining part, the green band, is the land sink, and that results in the substantial balance of the global carbon budget, and it also reflects the fact that land has been a very active player in limiting the extent to which the CO2 we emit from industrial processes and land use change stays in the atmosphere. For the last decade, the decade from 2010 to 2019, the pattern looks like this overall, with these really beautiful data from the Global Carbon Project. Emissions from industrial activity have been about 86% of the CO2 that's been emitted to the atmosphere, with land use change, deforestation, contributing about 14%. Of those emissions to the atmosphere, a little more than 40 billion tons per year on average, a little less than half has stayed in the atmosphere. We call that the airborne fraction. And the remaining, a little bit more than half, has been partitioned more or less equally between the oceans and the land, with about 23% on an annual basis dissolving into the oceans and 31% being trapped, at least temporarily, in ecosystems on land. And what I want to talk about for the remainder of the time is how to protect that 31% and, to the extent possible, increase it. So what are these background sinks? The first thing we should think as humans who need to live on this planet and want to tackle the climate crisis, that we're receiving a massive free subsidy from nature. Both the ocean and the land sinks are massive subsidies that we're not paying anything for, but are removing more than half of the CO2 we emit on an annual basis. Some aspects of the mechanisms that are resulting in the carbon removal and some of the persistence of those processes are relatively well understood. We especially have a good idea of the physics that are controlling the ocean processes. But especially on land, some of the aspects are poorly understood, and we don't have a very clear sense of the vulnerability of this background sink, especially on land, to a changing climate or to changing land use. So the major questions that need to be addressed are the sinks on land headed in the direction where they'll eventually saturate or potentially even reverse and result in carbon releases to the atmosphere? And how sensitive are they to climate change? Will we eventually reach a level of warming so great that the land sinks cease to function as sinks, or even more worryingly, if they transition to sources of CO2 release from the land to the atmosphere? And then it's also really important at this juncture to begin thinking about what are the prospects that we have for protecting these background sinks. Let me present a conceptual model that allows us to think about these sinks and the extent to which we can potentially enhance them. And I like to think about it in farming terms as the contrast between a silo and a haystack. A silo can store an amount of grain until it's full, and then that's its capacity, and it can't store anymore. A haystack, you can continue piling hay on and on and on until the haystack grows indefinitely. And what we would like to know is whether this background sink functions as a silo or a haystack, whether it has a set capacity that was fixed, for example, by historical deforestation, or whether as long as the atmospheric CO2 continues to increase, we can continue to add carbon to the terrestrial biosphere as a result of its essentially unlimited capacity. Of course, at the same time, we need to begin to think harder and harder about the consequences of climate change that might result in carbon losses from the terrestrial biosphere through mechanisms such as wildfire, insect attack, or widespread mortality of forests from drought. And the big implications of whether the terrestrial sink operates as a silo or a haystack for its potential magnitude going forward. If the silo model, the conceptual model, is fundamentally correct, the capacity of the terrestrial sinks might be on the order of 100 billion tons of carbon dioxide, something like 2 years of current emissions. But if it's more of a haystack model where the growth of the sink is fundamentally controlled by how much carbon pollution we put in the atmosphere, it could be substantially larger. It could be as much as 1,000 billion tons of CO2. Remember, in the context of the budget we talked about, where for 1.5C we only have 320 billion tons of CO2 emissions remaining, these are very, very big numbers. So one way to begin to distinguish whether the silo or the haystack model is more correct is to ask, well, if it is a silo, that implies that volume in the silo was created by deforestation, by past carbon removals, but it also implies that the historical sink, as we've been able to reconstruct it over past decades, is already partly filling up the silo. So looking across all the literature, the estimates are that human activity has probably released, as a result of land use change, something like 800 billion tons of CO2 from the land surface to the atmosphere. We know that there has been a persistent land sink over more than a century, and if we just add up that last sink over the century or so that it's been operating, we can see that it amounts for nearly 500 billion tons of CO2 uptake. So if the silo model is correct, the implication is that the remaining capacity of that silo should be something like 300 billion tons of CO2, and after that, it would be unlikely to be able to accept more. If that's the model, that means that the ability of this background sink to continue to absorb emissions from industry and land use change is going to be very, very limited. So let me just start out with a conclusion here about what we can do to protect this background sink. And there are really three things we can do to protect the background sink. The first is to limit the amount of climate change that occurs. It is totally clear that the elements that are inserting vulnerability into the operation of this background sink are a warming climate and its effects on the ability of forest and grassland ecosystems to sustain normal levels of productivity. The second thing we can do is also limit climate change, and the third thing we can do is also limit climate change. That is our primary and our most potent weapon for maintaining this background sink, a key element in supporting nature's role in tackling climate change. It is, in fact, nature's biggest contribution to climate change solutions, and it occurs for free without us doing anything except redoubling our efforts to tackle climate change. Let me spend the rest of the time speaking to this question of what we can do to enhance the carbon uptake in terrestrial ecosystems. And it's a topic that is often described as natural climate solutions. So for natural climate solutions, there are really two categories of things that we need to be thinking on and working on. One category is in the area of decreasing emissions. That means decreasing the amount of deforestation, as I said, mainly in the tropics, improving the way we do agriculture so that soils can lose less carbon, and being really attentive to other land use, especially protecting coastal ecosystems. The second category of efforts we can be undertaking concern increasing removals. We know that growing a forest actively removes carbon dioxide from the atmosphere. We know that effective stewardship of soils or conversion of grassland soils from agriculture to prairie can play a huge role in increasing their ability to take carbon from the atmosphere. So we can increase removals through improved management of forests, cutting them less often, reforestation, regrowing forests where forests had been previously growing but had been cut and areas had been converted to other land uses, afforestation, which is introducing forests into areas that hadn't historically had forests, and that's been successful in some places. Soil stewardship, being more careful with things like plowing and soil amendments and cover crops, and restoring coastal ecosystems. There's a substantial potential for activating nature to provide climate solutions through both these approaches. Natural climate solutions have a number of additional benefits that can be really important. Many of our most important opportunities for conservation also involve decreasing emissions from human activities and deforestation. They're deep opportunities for win-wins where the climate benefits, but we can also achieve important benefits in terms of biological diversity, in terms of the habitat quality, in terms of ecosystem goods and services, things like fresh water and clean air, and also important win-wins in terms of indigenous and rural communities where their lifestyles depend on healthy ecosystems surrounding them. But there are also some challenges that are associated with delivering these natural climate solutions. One is that lots of development pathways are cut off by that. Second is that growing healthy ecosystems requires the land to be dedicated to that and that the water resources be available. And it also implies a fundamental and maybe even ethical commitment to supporting some kinds of lifestyles over others. I believe that we have the opportunity to take advantage of the win-wins while limiting the risks of downsides and costs, but we'll need to be very strategic about the way we do it. What's the potential for these natural climate solutions? There have been a whole bunch of studies that have tried to address this. The most widely discussed one was published by Bronson Griscom and colleagues in 2017, and it shows the potential carbon uptake in terms of billion tons of CO2 per year for something like 20 different strategies. The top 6 are all in forests, and they're reforestation, avoiding deforestation, improving forest management, improving plantations, avoiding fuel removal, and managing wildfire. One of the really nice things that Griscom and colleagues did is they said, well, how much of these solutions are available at different carbon prices? How much is available at a very low price of $10 per ton of CO2? How much is available at a kind of a realistic price of something like $100 a ton of CO2? And how much is available if you had an unlimited amount to spend? And the white part of each of these bars is the unlimited part. The light gray bars are the $100 a ton, and the dark gray parts are the $10 a ton. Griscom started kind of a land rush where everyone said, wow, if these natural climate solutions are so cheap and they're really substantial quantities that are available for carbon prices as cheap as $10 a ton, why should we bother with decarbonization? We'll just solve the problem by increasing the CO2 uptake in land ecosystems. And he didn't mean that. And the paper doesn't really say that. What the paper really says is that by careful application of sophisticated management, we can store meaningful amounts of carbon in land ecosystems at a carbon price of $100 a ton or less. And the price estimates are, of course, very uncertain. And none of them account for the political and institutional challenges that are associated with managing these ecosystems, especially in countries that don't have strong governments or a strong tradition of ecosystem protection. Also, there are lots of other studies that reach different conclusions from Griscom and colleagues. Last year, people in my lab published a study of all of the estimates that have been produced so far on the total capacity of carbon removals that we might achieve from natural climate solutions. And there have been something like 40 studies published, and we arrayed them from the biggest to the smallest. The Griscom study is one of the biggest, and plotted them on a scale that has a broad orange band that indicates the amount of negative removals that the Intergovernmental Panel on Climate Change says will be required in order to have a 66% chance of limiting warming to 1.5 or less. And there are a few studies that indicate the potential of natural climate solutions being in the range where it might be able to provide that level of removal, but most don't. Most estimate much lower levels of removal that are on the order of a few 100 billion tons of carbon dioxide forever, closer to the end of the silo scale than the haystack scale that we talked about earlier. And returning to the picture of how much carbon loss there's been as a result of land use activity, how much land sink we've seen since 1850, we can ask how all of these studies compare to the difference between the two, which is around 300 billion tons. And if all the other studies are emphasizing this silo model of the way that terrestrial sink works, we'd expect the average estimate of CO2 removal potential to be on the order of 300 billion tons. And this is a plot of the removal potential of all of the studies that you saw on the previous chart. And what you see is that the average is between 300 and 400 billion tons, indicating that most of the studies expect substantial and an important, but not an overwhelming amount of carbon that could be removed as a result of these mechanisms for natural climate solutions. I want to spend just a few minutes now putting all this in context and asking how we can harness markets in order to drive forward the agenda of natural climate solutions. So what we can say about natural climate solutions is that, first of all, it's important to remember that they're just fundamentally different from emissions reductions. And the main reason that they're fundamentally different is that when carbon dioxide is removed from the atmosphere and stored in vegetation or soils, the risk of a future release is actually increased as opposed to emissions reductions from, for example, converting a coal-fired power plant to photovoltaics are decreased by having the new technology in place that has the potential to even expand its application as its validity and reliability is demonstrated. So in particular with natural climate solutions, we face three key problems. The first is permanence. Will the carbon that's stored now still be there in 10 years, in 100 years, in 500 years? Or will it be released by a fire or an insect attack? The second challenge we face is leakage. Especially with forestry projects, it's hard to know whether protecting a forest here just makes the loggers go to a forest in another part of your state or another country or even on another continent. It's a very difficult problem, and it's one that looks very different from the perspective of the carbon balance than it does from the perspective of conservation efforts to protect a particular species or ecosystem. And then the final challenge we face is called additionality. How do we know that if there is a market and a forest producer is paid for protecting the carbon in that forest, that the additional carbon is a result of our payment and that the landowner wasn't planning on protecting that anyhow? And this particularly comes into focus in areas like national parks, where there is at least a nominal commitment to protection. Maybe the protection's incomplete, and it's hard to know with a carbon payment whether that has protected all the carbon, half the carbon, 10%. So how can you use markets in this context? The first thing to know is that there is just surging interest in carbon markets. The recent magnitude of that has been around $300 million per year, but it's expected to grow to about $700 million within the next half a decade. There are also growing worries about these carbon markets, and they tend to be of limited transparency, questionable quality in terms of being able to identify the amount of carbon that's been stored in each ecosystem and with each payment. Often protections are limiting or lacking, and if the carbon is released as a result of any kind of land use or disturbance, the owner is left basically holding the bag. And there's been a race to the bottom on price as companies around the world have been more and more interested in purchasing good-looking, or whether they're really reliable carbon credits at acceptable prices. And this race to the bottom has meant that lots and lots of the products that are now on the market really don't have the characteristics that we need in order to have confidence that whatever payments are being made for these products are actually resulting in the removal of the agreed amount of carbon from the atmosphere. There are now carbon removal projects, carbon offset projects around the world. We're seeing them in essentially every continent, and the amount has been growing rapidly. It's really surged since the Paris Agreement, when it was clear that offsets could be widely applied to not only nations meeting their nationally determined contributions, but also for corporates who are increasingly interested in being able to document that they're operating at net zero carbon for part of their corporate social responsibility. At the same time, we have a much better idea of how long carbon lasts in forest. And on average, carbon lasts a really long time in the tropics, but the persistence of forest carbon in much of the temperate zone is actually quite short. And this historically, forests were disturbed by insects or they were disturbed by fire, and the expectation of storage that really lasts for hundreds of years is deeply challenged by this historical record of just how forests behave. And of course, in many places around the world, in Western North America, in the Mediterranean, in Australia, we're seeing a massive increase in the loss of carbon in forests to wildfire. And it's really hard to figure out how to create a system in which we're protected against the risks of wildfire, not only in human lives, but in terms of having a market that's robust against those changes. Leakage is a really big problem. because the forest products markets are increasingly international, and it's hard to know even whether effective forest protection in a place like Borneo, in this picture here, doesn't just mean that the loggers go to South America or Africa in order to do the deforestation. And additionality has really been the biggest challenge, and here's a selection of recent headlines about the additionality crisis. And I would say that the sense, growing sense in the public is that captured in this headline that says carbon offsets are a scam, and that we really have almost no credibility that an investment in protecting forest carbon actually protects that carbon. So I want to close by proposing a solution. It's a solution that's simple, but I think has the potential to be entirely robust. The essence of it is to promise less and deliver more. So we know that forests can be incredibly important in removing CO2 from the atmosphere, and we know that we can enhance that removal, but we don't know that we can deliver high confidence on permanence, on leakage, or additionality. But what we can do is offer carbon products with large buffer pools. And the idea of a buffer pool is that if I grow a forest with 10 tons of carbon, I might sell 2 of those tons, but be required to put 8 of them in essentially an insurance account, so that if something happens to the 2, it could be paid back. If we spread this buffer pool over all the producers around the world, if we are careful about managing the size so that it is scaled to the risk, it can really make a huge contribution. The other thing that we can do is issue partial credit to address additionality. If a forest has some level of protection, but that protection is not known to be complete, there's still carbon to be protected, and we should do our best to invest in protecting it. But whoever purchases those carbon offsets shouldn't get credit for the whole forest. That purchaser should only get credit for the additional confidence that was inspired by the payments. And the same thing with leakage. We don't have any kind of an international jurisdictional system that can precisely measure what leakage is, but we need to recognize it's real and recognize that carbon payments for leakage or carbon payments for carbon offsets need to recognize that some of that will leak out. We also need robust standards. We need to be sure that the standards are science-based, that they're public and transparent, and there need to be credible actors who are involved as verifiers and insurers. And then the third thing we need is real community engagement. This can't be done just by landowners. It can't be done just by governments. It can't be done just by conservation organizations. In particular, it needs to create conservation-friendly economic opportunities that engage indigenous and rural communities and recognize the role of governments at all levels, cities, states, countries, and international agreements to provide jurisdictional oversight. There are lots of groups that are now implementing some of these steps, but they're mostly implementing them in the direction of trying to improve the quality rather than trying to improve the insurance. And I think in many ways that's taking us in the wrong direction. It's pushing us away from the most important conservation opportunities toward the kinds of forests, especially plantation forests, that are easiest to monitor. Well, what we really need to do is boldly tackle the conservation challenges that are associated with protecting the world's most important conservation targets, especially in the tropics. So what is the promise of natural climate solutions? We can use natural climate solutions to help us fight the climate crisis. We can also use natural climate solutions to help conserve some of the world's most important areas. And finally, we can use natural climate solutions to help protect communities around the world. But we need to recognize that the potential for that is limited and that our most powerful tool in attacking the climate crisis is decarbonizing industry and agriculture. Nature's role in climate change solution is, number one, protecting background sinks, which we can do most effectively by decreasing the amount of emissions from industry, agriculture, and energy, and by deploying natural climate solutions which have real potential to deliver benefits for climate, for communities, and for nature. Thank you very much. And again, I take great pleasure in extending my thanks to the JapanPrize Foundation for the privilege of addressing you all.